All right, any other questions? I assumed that there were none, so I started up the video over again.
Yeah.
Right. All right. Forces. This is the first bit of material for chapter 1B. There are certain forces that we will deal with regularly, and so we'll just start out with a list here. Sort of a checklist. So when you're going through looking at force analysis, it's helpful to be able to at least go, all right, so what do I need to consider? Now I've got a really long one that we'll add letters as we go. That's what I'm heading towards. All right, so F is for friction. T is for tension. O is for other. N is for normal. G is for gravitation. The symbols that I use for friction, I use what I refer to as the Baroque F. It's just a fancy lowercase f with a little extra curl in there. For tension, I use F with the subscript T. I used to use a capital T for tension in the diagrams, but we will get to a point near the end of the course where I need T to stand for period, as in the time. And I don't want to get to that point and go, all right, we're now having T stand for something completely different. And usually from context, it works out okay, but there is a relationship between period and tension in certain situations, so F sub T. N, I use a capital Y for normal force. And you might be wondering, where does Y figure into it? My high school physics textbook used a capital Y, and we don't use capital Y for anything else. Gravitational, there's two different symbols depending upon the situation. What we will deal with right now, it is a lowercase w for weight, W-E-I-G-H-T. Or if you're talking generalized gravitational force, such as between planet and sun, or between you and the desk in front of you, F with a subscript G. So in order for there to be a friction force, you must have two objects touching. So requirements, there's contact and desired relative motion. So just because two objects are touching each other does not mean that there is a friction force, but there has to be a desire. So right now, assuming that the floor is level, there's no friction between the table and the ground. However, if I push on the table, there's now a desire for the table to go that way. If the floor were frictionless, the table would move. So now there's desired motion, so now friction is involved. Tension, there must be a tight, or for whatever reason, use the word taut here, taut rope, chain, string, whatever happens to be pulling. Normal force, the requirement is contact. Gravitational force, the generalized, gravitational force in general requires two masses. There's a gravitational force between any two masses. But specifically, weight is involved if one of the masses is small, I'll put small in quotation marks, and near in quotation marks. a huge mass. So in this context, the huge mass is a planet or a moon or something of that size. A small mass would be, well, pretty much anything that you can find on Earth other than the Earth itself. So an elephant would be considered small.
So like an example of tension was like the first experiment we did when we both pulled the rope and then she pushed it
Yes.
down a little bit. Okay.
Yep, definitely tension involved there. And when she pushed on the rope, she was applying a normal force.
Okay.
A normal force is what keeps you from falling right now. The chair is holding you up. If the chair disappeared, you would fall because the gravitational force is acting. But if the chair got pulled, the normal force would go away and you'd be in free fall.
Question.
Yes.
First, can you not stand directly in front of all the words? Second question. So tension only requires like something being taught. There's like two.
Yeah. There's a pulley.
Okay, pulling specifically. I just want more words to go off of.
Now, in physics, there are not a lot of times that you can get away with always, because there's usually some bizarre little exceptions. Oftentimes it's anything you would ever experience, it's an always. And this is anything you would experience unless you get into theoretical physics, advanced theoretical physics even. It's an always except for that. Black on black. There we go. Forces always come in pairs. For the sake of this course and the next course, treat this as a golden rule. Each force in that pair acts on a different object. In opposite directions. But are the same type of force. And same magnitude of force. In other words, if I have a friction force, I have another friction force acting on a different object. If I have a normal force, I have a normal force, another normal force acting on a different object. Yep, Laura?
Okay, first clarification. What's the word after the word same something force at the end?
The same type of force and same magnitude of force.
And then my other question is, so for gravitational force, if we're looking at general gravitational force, the only requirement is two masses.
Right.
But for weight, it needs both two masses and that.
Yes.
Okay, I just want to make sure we're done. Thank you.
Yep. Other questions right now? Force direction with respect to other in. Oh, I have conveniently skipped over other. Let's back up for a second here. The requirement for other is typically it's stated in a problem, but ultimately it comes down to we don't know, or from a physics point of view, care what the source of the force is. So the requirement, don't know, or don't care what the source is. I have a box with a 3 Newton force pushing against it. That's an example of other. What's causing the 3 Newton force? I don't know, it's irrelevant. So we don't know what it is, and we really don't care what's causing it, because the problem just deals with, there's a 3-Newton force. When doing a force diagram, which we're heading towards, other is the one time that you only will do one of them. You would not do that in pairs. All the rest you would draw in pairs. And this, what I mean by drawing the pairs will become probably brutally obvious when we start doing the force diagrams. But if I have friction, the pair of forces will be anti-parallel to each other, sort of side by side. Pair of tensions will always point towards each other. Other is problem dependent. Well, there's no pair, so I guess not applicable. The normal force will always point away from each other. And gravitational force always points towards each other. Yes, Riley?
What does it say at the top there? Force.
Force direction, DIR,
Oh,
with respect to other in pair.
okay. I think.
And now force direction with respect to the objects. So friction wants to oppose the desired relative motion. So it opposes desired relative motion and is parallel to the surfaces of contact. So in the case of the table and the carpet, the surfaces of contact is horizontal, so when I apply a force, that friction force is acting parallel to that. So on the table, it's pushing this way, and on the rug, it's going that way.
Question.
Yes?
For tension, wouldn't the arrows be facing opposite of each other since they're both pulling in opposite directions? If like,
The pair of forces, if I happen to have a string right here, which I will attach to the notebook. Or not. There we go. As I'm pulling on this, I got a tight string here, so there's a tension involved. The force that I apply to the string is this way. The force the string applies to me is that way. And so if I drew the force diagram, I'd have an arrow pointing this way on the string and this way on me. So they're pointing towards each other.
Does that say opposes desired relative motion and it parallel to the surface?
Surfaces of contact, yes.
Okay. Thank you.
Tension, parallel to the taut rope, chain, whatever. Other is problem dependent. Normal force, it is perpendicular to surfaces of contact. So I mentioned earlier, there's a force holding you up. It's the normal force from the chair exerted up on you. Likewise, you were pushing down on the chair. Why is it called normal?
Because it's perpendicular.
Yes, it is a math term meaning perpendicular. And gravitational force points toward other objects center of gravity, or center of mass force.
Could you, I'm sorry, I can't see. What does other say?
Problem dependent.
Okay.
So when we do the force side, sorry, puberty. when we are doing the force diagrams, I will ask you, if you're wondering whether other is one of the forces involved, I'd say, is there any problem that I mentioned where I didn't give a source, or hand to God, any mystery force involved? And if there is not, then there is no other.
Points toward other objects, what mass?
Points towards other objects' center of mass. All right, questions here before we start out in the exciting world of force diagrams.
60 seconds to write down all of that.
Okay, well, while you're doing that, why don't I just set up the problem?
Sure.
The first one's called box falling. I used to skip over this one, but this actually is the simplest of them all, and then we get into what's coming after this, box on ground.
It's a series.
So the first thing I'm gonna do is I draw a picture of what's going on. Now, I'm not worried about air resistance right now, but that's just indicated it's going through air. They've got some streams of this non-existent air behind it, and then ground. Now, when I remember, you can tell the ground because I've got these little hash marks. These little hash marks are indicating we have an object that we are considering to be still. You assume the ground is not moving. Right now, flat Earth works. We will get into round Earth in chapter 6. So first step, draw the problem. Second step, draw the two objects involved. Because I need space. I need to draw these someplace so that I can put my arrows on it. So I draw my box here, and draw the ground there. This is where my workspace is. Usually you will not have this much space involved as we get into, but separating the two objects so you have room is useful. So, are there any of these forces that we can eliminate from the problem?
Tension?
Yes. Why is there no tension?
There's no pulling.
Okay. Anything else we can get rid of?
Friction?
Why?
There's no air resistance. There's no air resistance, so there's no friction on the air. So
And what about the box on the ground?
like the box on the ground.
Once it hits the ground.
But the box is not touching the ground. There's no contact. So, all right, so friction's gone. Anything else?
Normal.
Why not?
It normal just requires contact.
Yep, the normal's gone.
Other.
Why are we getting rid of that?
There's no third force acting on us.
Yeah, I mentioned nothing about anything else, it's just a box falling. All right, see how easy these are? Just eliminate 80% of it right there. All right, gravitational force. Which way is the gravitational force acting on the box?
Downward.
Yes. So the Earth is pulling down on the box, so I'm gonna draw my arrow exactly that way, down on the box. So I draw a little arrow right here, and I label it. Put a little W for weight. But forces come in pairs, so there's gotta be another weight force pointing upwards. Well, if the ground is pulling down on the box has gotta be pulling up on the ground. So, done. First force diagram.
Can you explain how the box is pulling up on the ground? How does
Why
that?
not? Gravitational force requires two masses. I have two masses. I have the ground, I have the box.
Uh-huh.
It's not like nature looks at these two things and go, well, Earth's bigger, so it doesn't behave by the same rules. No, the rules apply to the Earth, just like they do to the box. But the Earth is so massive I looked at the calculation, if I jumped off that table onto the ground, the earth should move about the size of a proton.
Could you do it just to demonstrate?
What, jumping down the,
Yeah.
well, when you actually leave here, you can sort of bounce down the steps safely. And that earth comes rushing up toward you. Now these are just two objects, the rules have to apply to both.
So basically, like the box is pulling on the earth, but since that the earth has a larger gravitational pull, we don't see the box pulling the earth. Is that what you're saying?
No, they have the same gravitational pull,
Okay.
but the earth is so much more massive, you don't notice it. If I had an ant in front of me and an elephant, I could easily push the ant and not the elephant. I could apply the same amount of force to both, but the ant's gonna feel it more.
Okay.
So, the earth pulls on me with about 220 pounds of force. I pull on the earth with about 220 pounds of force. My mass is about 100 kilograms. The earth mass is on the order of 10 to the 24th kilograms. So it is not gonna be as noticeable. Matter of fact, I don't even think we have any equipment that would notice it if I jumped, how much the earth would move. Laura?
So in this scenario, the reason why we're not using general gravitational force, FG, is because the box is so small compared to.
Yeah, and near the surface of the earth.
Okay.
And you can tell it's near the surface of the earth because I made the earth flat with the box there. If we were talking more generalized, I would have the round surface of the planet. All right. Are we ready? Oh, rookie mistakes. I will give them a number now, but I haven't codified it to the point where my rookie mistake number 1 is always the same. But here's rookie mistake number 1. No man's land. I've seen this way too many times.